Okay, so let's start. Last time, Professor Lachowski finished sequence diagrams. Now we'll move on to the next part, use case partitioning. So each use case is divided up into a collaboration of three types of classes: boundary, entity, and control, as you saw before. So a boundary class contains the functionalities depending on system's environment. That is either the human user or the external system. So it's the interface to the environment. If it's a human user, then it's the graphical user interface. If it's the external environment, then it's the file format you use to exchange information with the external system. So entity classes are functionalities dealing with storage and handling of information, i.e. the database. Control classes deal with functionalities specific to one or a few use cases and not naturally placed in boundary or entity classes. So these are the glue logic for each specific use case for coordinating the actions, the messages that pass between the boundary and entity classes. So the goal is to achieve localization of changes so as to result in a stable system. So localization of changes means that if you change the internal implementation of one of these classes, it doesn't affect the other classes. So for example, if you adopt a new fancy graphical user interface, it doesn't change the doesn't have any effect on the entity and control classes. Similarly, if you change the entity classes database, you don't have to. It doesn't change the boundary classes. So, therefore, the system is stable and makes the system maintenance and upgrades easier. So we need to make judgments as to where to place the functionality. Most decisions are very obvious, but some parts can be a little fuzzy, especially for the control classes. Sometimes you can merge it with the boundary classes. So here's the example for the select course to teach use case. How do you partition it into multiple analysis classes? So the use case is select courses to teach. It's represented as the oval. And in the analysis model, we have this dotted oval, which indicates a use case realization. So, as opposed to the solid oval, which indicates the use case itself, there's a relationship trace between the use case realization and the use case, which means that you should be able to trace from the realization to the use case. It's the traceability between analysis model and use case model. And this particular use case realization with the same name as the use case consists of all these different analysis classes: one boundary class, one control class, and 5 entity classes. So participant means that all these classes participate in the specific use case realization. This participant is actually applied to all of these links, not just for the one. We just didn't draw it in the diagram. So here's the how the associations are drawn in the between the analysis classes. So you have 5 entity classes representing the database entities. You have 1 user interface class. 1, 2, 3, 4, 5. That's another entity class, and 1 control class. So, and an actor. Remember, actor is another class. All these classes just have different stereotypes. That is, different funny shapes. Notice also that you have a professor actor class and also a professor entity class. As we discussed before, it is very normal. So the professor actor class represents the human user, while the professor entity class represents the user's entry in the database. So this is a very typical collaboration pattern where the control class sits in the middle, while the boundary class connects to the control class, and the control class connects to the entity classes. So, and the connection is one way, as indicated by this arrowed connection. So, especially for the connections between associations between the control class and the entity classes, it is very important that the association be one way. So, for example, this one, all these 5 associations are one-way associations because the entity classes are supposed to be passive. That is, they're not supposed to hold references to the control classes, but the control classes should hold references to the entity classes. Therefore, you can refer to the entity classes from the control class, but not vice versa. This is to encapsulate the entity classes. So this diagram is the high-level overall view of the entire system in terms of the analysis classes. So this is the use case realization as a collection of analysis classes for the select courses to teach use case. So you can see you have, this is just a redrawing of the previous slide, where you have an actor, professor, you have a boundary class, you have a control class, and you have a whole bunch of 5 entity classes. And so this just says you should never draw this diagram in the requirements or in the analysis document. This is just for the illustration purposes only. Of course, you can have another use case realization. For example, register for a course. So you have a actor, boundary, control, and perhaps these. So what I have in the black circle is the analysis classes involved in the use case realization for students register for courses use case. You may have others like register, prepare course catalog, for example. So you can find out all these classes, analysis classes for the use case of prepare course catalog. So you can find other use case realizations here also. So the purpose of this diagram is just to show you that all the use cases, they actually interact mainly via the entity classes. As you can see, both the students register for courses use case and professor select courses to teach use case. They all access the course, section, semester, course offering, these common entity classes, even though they have different boundary and control classes. So it is a very common pattern, as you'll see in later in your exercises for identifying the analysis classes. So now we move on to the component engineer's job of analyzing classes. That is, so up to now we have been focusing on collaborations between classes, boundary, how they talk to each other, boundary, control, and entity classes. Now we're going to focus on each individual class, the internal details of each class, how to express that. So, analyze classes. So you identify responsibilities of each analysis class. Find out from the roles that a class plays in each use case realization by considering class diagrams, that is the domain model, sequence diagrams, as Professor Lachowski discussed last time, and flow of events as part of the use case specification. So you can use CRC cars. That is a particular way of analyzing classes, which we'll discuss in the next slide, to discover the responsibilities. So, and then you identify the attributes for each analysis class. So, for boundary classes, the attributes are items manipulated by actors, because the boundary class is the interface between the actor and the system. Therefore, whatever the actor manipulates, like what he enters on the user interface as input to the system, or what he gets as output from the system, these should form attributes of the boundary classes. For example, for the professor interface boundary class, perhaps you need to have attributes like semester, course to teach, course offering, etc. Entity classes, the attributes are easy. Just get them from the domain model. Whatever the domain model has, you place the attributes in the entity classes. For control classes, they rarely have any attributes. Sometimes even if they do, they're usually temporary attributes, like a counter, something that's transient. That is, when you finish using the system and log out, all these values are lost. They're not important. They don't need to be stored. Or unlike the entity class attributes, where any change to them must be updated to the database. So try to infer as much of these attributes from the use case descriptions, including the flow of events. So then identify associations between the classes. So from messages in the sequence diagrams, so class A is sending a message to class B. That's a clear indication that you should have an association from class A to class B. Notice that associations can be directed, can be one way, or it can be two way. So if class A only sends a message to class B, while class B cannot send a message back to class A, then it's a one-way association from class A to class B. And from shared and common behavior among analysis classes, these are useful for identifying generalizations, right? If something is common, you pull it out into a common superclass. So these relationships are not real-world relationships, but relationships that must exist in response to the demands of various use case realizations. So the relationships in the domain model are real-world relationships, right? Professor teaches a course, student takes a course, but the associations, aggregations, and generalizations in the analysis model, they're not real-world relationships, but they're really useful for the software engineers for their later implementation of the system. That is, especially for control classes, they do not correspond to any real-world entity. They're just there to facilitate the interactions among the other classes and to ease implementation in the future. These relationships are really for the software system implementation for the software engineers, not real-world relationships that you discuss with the client, for example. So this is the CRC cards, classes, responsibilities, collaborations. So in the old days, you really have these cards, 3 by 5 inches, and you when you design your class analysis classes, you actually write down class name, responsibilities, and collaborators. So responsibilities are tasks that the class is required to carry out. So they become one or more operations on the class. And collaborators are the classes that are used to carry out the tasks. They become the associations in the class diagram. So it helps us to think objects, that is, think in an object-oriented fashion. So you should try to avoid having too many responsibilities in one class. If so, you have low cohesion. So cohesion is this metric for measuring how cohesive a class is, how focused. If a class does one thing only, it's very cohesive. If it does many things at the same time, it is loose. That is, it has low cohesion. So try to achieve high cohesion when you design classes. And try to avoid having too many collaborators for any given class. If so, you have high coupling. That is coupling between this class and other classes. So you should try to achieve high cohesion and low coupling to promote modularity in your design. Of course, you should have some coupling. Otherwise, the system wouldn't work, right? You have to have some degree of coupling, but you should try to minimize the coupling. There should be at most 3 to 5 responsibilities for each class. to avoid having a class with too low cohesion. That is a so-called scatterbrained class, a class that does many things at the same time. So, of course, CRC cards, you can use it as a conceptual design tool. We don't really have these physical cards anymore. So here's the CRC card for the control class select courses to teach manager. Remember, this is a convention that you have MGR manager at the end of the class name. It indicates it's a control class. It's called a manager because it manages interaction among the other classes. It has responsibilities of retrieve course offerings, retrieve teaching schedule, create teaching schedule, update teaching schedule, 4 responsibilities, and different collaborators depending on its different responsibilities. For the retrieve course offerings responsibility, it has these collaborators: semester, course offering, section. And for the update teaching schedule, responsibility has section, professor as collaborators. So you can determine this information by examining all of the sequence diagrams for the use cases in which the class plays a role. So in the notice the keyword all of the sequence diagrams, because this particular control class may play a role in multiple sequence diagrams. You must examine all of them. For example, create teaching schedule. Responsibility is identified from the sequence diagram, create a teaching schedule, and update teaching schedule is perhaps identified from another sequence diagram. So you must examine all of the sequence diagrams in which this particular class plays a role. So, and these collaborators obviously turn into associations between this control class and all of these entity classes. And as we saw before, this association is one way, from the control class to entity classes. Remember, never have an association from entity class. Entity classes are supposed to be passive. They always have associations pointing to them, but not from them. So, now we discussed how to identify attributes and operations and associations. Now we discuss something else we never saw before. This is state machines. That is, all the attributes and operations are there, but they're rather static. That is, they tell you what the object can do at runtime, but they don't tell you exactly how the object behaves dynamically. So this is the job of the state machine diagram. So it describes the behavior, the runtime behavior inside an object, what an object does when it receives a message. So it is a directed graph, which means that the edges have directions. That shows the states and events. The states are modeled as nodes, and events are modeled as arcs or edges. Events that cause state changes among the different states. It shows all the messages that an object can send or receive, and this describes all the possible states an object can get into during its lifetime. It is drawn for a single class to show the lifetime behavior of a single object, as opposed to sequence diagrams, which shows the collaboration behavior among many objects. So this is a localized view of a single object. Of course, it should be consistent with the sequence diagram. So if a sequence diagram shows an object as sending a message or receiving a message, the state machine diagram must reflect that. It must be able to accept or send a message consistent with the sequence diagram. So here's one example of a bank account class. So you have essentially these states. So this particular state indicates the initial state. This is when the object is initially created with a new operator in C++. You go from the initial state to in credit. That is, this particular transition here is taken as soon as the object is created, and this is the final state. That is the state when the object goes into at the very end. So you have these states. So you have initially the bank account is in the in credit state. It means that this account is in good credit standing. And when the balance is goes below 0, it goes into overdrawn stage. And when the balance goes above or equal to 0, it goes back to in credit stage. And when it's overdrawn for over 3 months without over 3 months with the balance always less than 0, then you go to frozen stage, and you send a message to the bank manager that says account frozen with the account number as the parameter. And if it's frozen but you put some money into it, so the balance goes above 0 again, you go back to in credit state. And while you're in the in credit stage, you receive a message that's closed account, then it goes into closed stage. When it's closed for more than 5 years, you go into the final state, and the object is deleted. So a state is represented as this rectangle. Sometimes it's drawn as a circle. Both are fine. Notice here it is not a class anymore, unlike what we saw before. This is just a notation. It's not a stereotype for a class. So a state is a time during the life of an object when it satisfies some condition, performs some action, or waits for an event. So it has a duration. That is, a state can exist for a few seconds, a few minutes, or a few years. A state may be characterized by the value of one or more of the attributes. For example, the bank account can be in credit or in a withdrawn state based on the value of balance attribute. If it's less than 0, it's overdrawn. If it's greater than or equal to 0, it's in credit. Or existence of a link to another object. So, for example, a professor object may be teaching or not teaching based on the existence of a link to a section object. So a professor object may have two states: teaching, not teaching. So how do you identify the states? You check for a link to a section object. If the professor object has no link to a section object, then it is in the not teaching state. Otherwise, it's in the teaching state. So Of course, you can add a Boolean attribute to the professor class that says teaching or not teaching. Then you can identify the state based on the value of the Boolean attribute with the first method. But if you want to save some storage space and not have the Boolean attribute, you can just check for links to other objects. So that's fine too. So we can discover object states from sequence diagrams. Typically, when you receive or send a message, it indicates a state change of the object, but not always. Sometimes a message only invokes some actions, but not cause a state change. So as we saw before, this guy indicates the initial state, that is the start, also called the start state. That is the state where the object goes into when it's first created. So each diagram must have at most one initial state. And you have the final state with this particular shape. You can have multiple final states depending on your messages you receive during the object's lifetime. You can go into different final states. So no initial or final state indicates a looping behavior. That is, the object is in an infinite loop. So typically infinite loops are bad in the program, right? You learned that if you have infinite loops, it means your program will hang. But here, infinite loops are okay. An object can be waiting for a message, and when the message arrives, it does something and goes back waiting for a message, and so on and forever. So it's okay because the loop, within the loop, it's waiting for something to happen. It's sitting idle. It's not looping like a while loop without while busy waiting. So loops are okay as long as you have a wait in the middle, especially for state machines, which is different from a sequential program that runs from start to finish. A state machine is supposed to be receiving and sending messages continuously for a very long time. States may be named. For example, you put an invalid name inside the state, or you can have unnamed states as anonymous states. So this is not very common. This is only for some transient states that are not important. Then you have anonymous states. Typically, states are named. Transitions are arrows. So it's a change of state from originating to a successor state, also called from target source to a target state. So they may be the same state. You may have a self-transition. A transition takes 0 time and cannot be interrupted. Of course, nothing takes 0 time, right? So what this means is that it's atomic. That is, when you take the transition from state A to state B, it always finishes before anything else happens. You cannot interrupt the transition in the middle. That's what it means of taking 0 time. It may take a very long time, as long as it's atomic. And triggers are the event that causes the transition to occur. So the event could be explicit or implicit. So implicit events may be if this particular state finishes its activity, then you have an implicit event that triggers a transition, but we'll see later. So event triggers a transition, and the transition is set to fire. So this is just a common terminology. When you take a transition and you fire a transition, it means the same thing. Also, we use the words event and message interchangeably. You can see an event or a message. They mean the same thing. So transition adjournments. That is the stuff you place near this arrow. These are adjournments. The transition include the event trigger, guard condition, and effect list. So the event trigger has event name plus any optional arguments, parameters. The guard condition is a Boolean expression which must be true for the transition to fire. So if the event happens and the guard is false, then nothing happens. The transition is not fired. Effect list is the atomic procedural expression executed if and when the transition fires. So notice the word atomic procedural expression. That is typically an invocation of the operations of an object. So this is the really consistent with the transition takes 0 time statement, because the effect list is atomic. Even if you have invocation of collection of operations, all of these must finish in an atomic step. You cannot interrupt them after you finish part of the set of operations. Event is something that happens at an instantaneous point in time. This is opposed to a state. A state, an object can be in a state for a duration of time, but event always happens instantaneously at a particular instant. So there are four types of events. Call event is a receipt of a synchronous call from an object that is a request that an operation be performed. So that is the synchronous call means that another object is calling an operation of this object, and this call must finish before a return message is sent from this object to the calling object. So the calling object is waiting for this particular call event to finish processing. So this is opposed to a signal event that is an asynchronous communication from an object. So call event is synchronous, signal event is asynchronous. So in this case, for the signal event, the sender object sends an event to the receiver object, and then the sender object can go on and do something else. It doesn't wait for the return event, return a signal. So that's the asynchronous communication. While the call event is a synchronous call, which means that the sender object must wait for the processing to finish before it can do anything else. So a change event is a specified Boolean condition becoming true. Say it is the keyword when with the followed by a parenthesis with a Boolean condition balance less than 0, for example. So the change event is different from a guard condition. That is, the change event is an active event occurrence. Whenever the balance is less than 0, this event is triggered. While a guard condition is something that's passive. so it describes the condition at the time when another event is triggered. So we'll see how this event, this is a particular change event based on the balance attribute less than or greater than 0. You can also have a guard condition with involving the balance less than or greater than 0. So we'll see some examples where you can express both situations. So time event is triggered by time. So for example, when date is equal to 2009 July 03 or March 07, depending on how you look at it. So this is a special type of change event. Whenever this condition is true, this particular time event is triggered. Or you can have elapsed time, that is after 10 seconds from the current instant, this time event is triggered. So both styles are possible for a time event. So events are processed one at a time. If an event does not trigger any transition, it is ignored. When does that happen? It happens when the guard is false, for example. Or if the object does not have a handler for the event, that is, the state machine doesn't have a event specification when it's in a particular state. So in that case, the event is just dropped, ignored. Only one transition within the state machine diagram may fire. So this is for a sequential state machine. We'll discuss concurrent state machines in the near future. So if two transitions can fire, then the choice may be non-deterministic. That is, you have a race condition. This is probably a specification error. That is, a state machine should be deterministic. At any given time, either no transition can fire, that is, the state machine stays at the same state, or one transition can fire. You should not have the case when you have multiple transitions are enabled and you can have multiple possibilities. That indicates non-determinism, and that's bad for as a specification. All state transitions must correspond to different events. That is, you cannot have one event triggering two or more different state transitions. That will cause non-determinism. You don't know what to do when the event happens, right? So one event triggers one transition, then it's deterministic. There are two ways to transition out of a state, automatic or non-automatic. So non-automatic is the typical one you see. One event happens, you trigger a transition. This non-automatic. So automatic transition happens even if you don't have an event. That is, when the activity of the state completes. So these are transitions without labels. So labels are event, action, guard. These are the labels. If a transition doesn't have any labels, then it is an automatic transition that happens immediately when the state's activity finishes. So we'll see an example of it later. So there are two types of actions. One is the action. One is activity. So action is instantaneous and cannot be interrupted. This is processing for transitions between states and exit entry of a state. That is, typically an event triggers some actions, and also entry and exit of a state triggers some other actions. Activity takes time to complete and can be interrupted. This is processing that occurs while in a state. So, I think examples would be good. So, possible forms of state behavior. So, a state can have no behavior. That is, it waits until an event occurs that exits the state. Or the state can have a event trigger with the guard condition and effect list. These are the arguments on the transition. When the event trigger occurs and guard condition is true, then effect list is performed. Effect list is a collection of actions. And do activity, that is ongoing execution of behavior while the state is an object is in a particular state. So this activity takes time to complete. And entry-exit actions. So the slides online has a typo where it says entry-exit activities. I'll place a updated version of the slides. It should be actions. So entry action is slash action is performed every time the state is entered, and exit action is performed every time the state is exited. So the dual entry and exit, these are keywords in UML, and all the others, activity and actions, are typically a collection of operations. So let's look at a so here's the one example of a state. So this is one single state in a particular state machine. So you may have, for example, you may have many other states. You have a state diagram. So we're just focusing on a particular state. Enter password. So you have a state name. Enter password. You have entry and exit actions. So upon entry, you set echo to start and clear password. That is, when you type in anything, it echoes back to the user as a collection of stars, and clear the original password that was in the text box before. Upon exiting, you set echo to normal. That is, after you enter the password, you go on to the next stage. You can set the echo to echo back in normal text instead of star. So both of these are actions, that is, they're atomic, cannot be interrupted. And you have internal transitions where upon receiving a key press event, you invoke the handle character action. That is, when you enter some characters, perhaps you check for its validity. For example, if the password cannot contain some special characters, you can issue an error message if these characters are entered. And clear, when you receive a clear event, you clear the password. When you receive a help event, you display help. So these events are perhaps triggered by the user pressing on the keyboard or clicking on the mouse, and you invoke these actions. So in this particular state machine, you have two entry and exit actions and 3 internal transitions and no ongoing activity. So here's the section class in the ASU example. It's a course section for a course. So you have initial state, and you have this transition to the open state with the action set enrolled, number of enrolled is equal to 0. So this is the action that's atomic, and this transition, if you notice, it doesn't have an event. It only has an action, right? So the syntax is that the event slash action. So this thing is a action. So this means that upon object creation, it initially is in the initial state, and immediately it makes a transition to the open state. Because this particular transition has no event, so it's automatic transition out of the initial state to the open state. And while in the open state, you have two event and action pairs. So add student, if you receive an event add student, you execute the action register with the parameter student, perhaps the student ID or the student pointer to the student object. And upon receiving the event drop student, you execute the action unregister student. So both of these are operations defined in the section class. Notice that these two events do not trigger any state transitions. After executing the register student action, the section object stays in the open state, in the same state. So upon receiving a registration closed event, perhaps issued by the registrar, or perhaps triggered by a time at the end of the add drop period, and this guard is true, number of enrolled students is greater than or equal to 10, so the guard is indicated as the square brackets. You make a state transition to the offered state. That is, the course section is now offered. So notice that this transition has no actions. You only have an event and a guard. And then you make a transition. You don't perform any actions. So upon receiving a registration closed event, with the guard, a number of students enrolled is less than 10, then you take the transition to go to cancelled state. So notice that the same event, registration closed, can trigger different transitions depending on the guards. So in this case, these two transitions are mutually exclusive, because these two guards enrolled greater than or equal to 10 or enrolled less than 10 are mutually exclusive. These two guards cannot be true at the same time. So this is a deterministic model. If you make a small mistake, say if you say less than or equal to 10, then this will be wrong, because if the enrolled students is exactly 10, you don't know which way to go, right? Both guards are true. So you should avoid that and to maintain determinism, so that these two guards are mutually exclusive. So in the cancelled state, you have these activities. So do / activity. So remember, activities are always preceded by a do keyword. So unregister all, delete schedule, delete self. So because these are activities, they take time to finish and they can be interrupted. Unlike the actions like register student, which cannot be interrupted. This is the definition of action versus activities. So why is that? Because unregister all essentially is implemented as a series of unregister operation calls. Perhaps call it for 100 times, call it for 8 times if the enrolled students is 8. So you may be interrupted in the middle while you are doing this activity. So this transition, when enrolled is equal to 40, then it goes to closed state. So notice that this transition has no event, unlike this one, which has registration closed event. So, and then while in this stage closed, when you receive a registration closed event with no guard, you go to offered stage. So when enrolled is equal to 40, okay, so notice the difference between these two. Enrolled is greater than or equal to 10 in the registration closed transition from open to offered. This is the guard. Well, this guy is an event. This is not a guard. This is when is the keyword indicating a time event. That is, when the enrolled number of students is equal to 40, when this condition becomes true, this event is triggered. So this thing is event by itself. While this thing, enrolled is greater than or equal to 10 enclosed in the square brackets, this is a condition. It's not an event. So notice the difference between these two with the keyword when. So and from closed to open, you have an event trigger drop student with the action unregistered student. So this is when the student drops the course. When the enrolled is equal to 40 and the course is full, it's closed. It doesn't allow any more registration requests. So notice that in the closed state, you do not have the add student drop student event action pairs. This means that if you have add student or drop student event arrive while you are in the closed or offered stage, you're not in the open stage, then these events are dropped. They're ignored. Only when while in the open stage and you get add or drop students, then you actually perform the actions. Okay, in the closed stage, the add student event is ignored, but the drop student event actually triggers the transition from closed to open. So, but in the offered stage, both add and drop requests are ignored. So, so notice also some events trigger state transition, some do not. So, for example, in the open stage, we will receive a drop student event. It stays in the same state. It executes the unregistered student action, and it doesn't go to another state. But in the closed stage, we will receive a drop student event. You actually do a transition into the open stage. It indicates that the course is now has less than 40 students and is open again. So both are possible. So this slide really has a lot of content. Any questions on this state machine? Yes.
So if we go to the over state, we never go to the end state, right?
Yes, that's true. So when it's offered, I think it stays offered. So the end state is typically used upon object destruction. That is, when the object is deleted, this offered state is kind of a sync state. That is, you can see that there's no transition out of it, right? I think it's really not very accurate. There should be a transition out of it. That is, you should be able to have a cancel transition, perhaps invoked by the register. Well, it depends on your particular system. If you do not allow cancellation of a offered course, then you do not have a transition. But if you do allow cancellation, for example, just after the add drop period, before the semester, well, it depends on your application requirements. Sometimes you may need to cancel offered course. Sometimes you may not allow it. So any other questions?
So is end state means the end of job or other meaning?
End state. So end state is the final state. That is, it indicates. Let me see. So it indicates the state of the object is in when it's typically when it's destructed. So in this example, the end state is the object. The state is in when it's canceled. So I think you're thinking, should this be an end state or not? Offered, if it doesn't have a transition out of it, I think it should be an end state. So let me see.
So can a state diagram stop without reaching the end state? You can see we reach offer here and we have no more transition.
Yeah, for this example, it is stuck in there, right? You have nothing there after you reach the offered state. You cannot transition out of it. So in that sense, it is a final state. Yeah, I think you can draw it at the end state as the offered state. So in that case, you can view it as having two end states. We discussed before, right? You can have multiple final states. So this course, this section object can be eventually canceled, or it can be offered. So I think really, to be more accurate, you should have two end states in this diagram. We just didn't draw the offer at the end state. So we have 15 minutes. Okay, so we can do another example. So this is supposed to be in-class exercise, but I think we're trying to push the progress of the lecture, so I just discuss it in, without having you do it yourself. So, so here's the domain model class diagram for the video rental video example. So we're focusing on the rental copy class. So it shows construct a state machine diagram. Also, this type of questions will be on your final exam. So construct state machine diagram showing the states that an instance of the rental copy class can be in with respect to its rental status. Show only the state transitions and events and conditions that cause the transition to be taken. Do not show the activities that can occur within the state. So this is for clarity. So here's the all the requirements that this particular object must be able to do. So you go through some analysis. So you can do this mentally. You don't have to write it out. So the system must be able to keep track of which movie videos have been bought, rented, and by whom. So the videos bought, the system must record the quantity bought. For the videos rented, the system must record which copy of the video has been rented and when it's due back. So you have two states, available and rented. And you don't have a bought, right? Because when it's bought, it no longer belongs to the video shop. You don't have to keep track of it anymore. It's gone. So, but it's rented, it may be returned, so you need to keep track of it. So, events are rent, and transitions are from available to rented, triggered by the rent event. So, system must keep track of overdue rental videos and send email notices to customers who have videos overdue. So the state is overdue. The event is when date greater than return date. Transition from rented to overdue with this event. Members must be able to make reservations to reserved, from available to reserved with the reserve event. So reserve a video without renting it. Reserved triggered by rent event, from going from reserved state to rented state. A member can reserve at most 5 movie videos at any one time, but there's no limit on how many movie videos a member or non-member can rent at any one time. So there's no state event transition information in this statement. This is a domain model requirement. Staff must be able to sell or rent videos and process the return of rented videos. So rented, when the particular rental copy is in the rented state or in the overdue state, and a return event happens, it goes to available state. Others are perhaps cancel a reservation and delete when it's in reserve state, you cancel, you go to available. When it's in available state, you delete it. You go to final state. Go to its final resting place. So it means that the video is deleted. You no longer offer the video, a rental copy for rent. So here's the diagram solution. So initial state with the transition. So So you may have some questions on. So this is the initial state, right? This black dot, but you have a transition with no guard, no event, and no actions. What this means is that you immediately go from the initial state to available at time 0. It's an automatic transition. So essentially, you can view the available as the initial state. Also, because theoretically, to be rigorous, you should say this is the initial state, and at time 0, you make a transition to available state. But sometimes, if you are not very rigorous, you can say available is the initial state, because it's pointed to by the from the initial state. So, of course, if the initial state transition has some guards or action or events, you must wait for something. Then you do not go to the available immediately. But in here, you go to available state immediately. So when you are in available, you receive a reserve event. You go to reserved, and when you are in reserved, you receive a canceled event. You go back to available, or when you receive a rent event, you go to rented. And available rent, go to rented. In rented, you get a return, go to available. And when you are in rented, when data is greater than return date, you go to overdue. And when it's overdue and you return it, go back to available. So when you delete it, it goes to the final stage. So perhaps the rental copy is damaged by the customer, so you delete it. And when you are here, you do not have any more outgoing stage, so you stay here. So that's a pretty straightforward state machine diagram. So notice that when you are in different states, different events are enabled. So when you're in available stage, you can handle reserve, delete, these two events. So and rent, these three events, right? When you are in the available state, you have these three outgoing transitions. So when you are in the rented stage, you have return and when time event. You have these two events when you are in rented stage. So you cannot have return or this time event in the available stage. If you have a return event when it's in available state, what does it mean? You're returning a video that's not even rented. It indicates an error in your specification. So, so any questions on the state machine? So we can create a composite state that's called unavailable. We'll discuss composite states next. So it means that it has three substates. When you are in any of the three substates, you are really in the unavailable composite state. So common errors are showing flow of control. So we'll discuss activity diagrams next. It's another way of specifying an object behavior. So do not show flow of control, and also show state transitions events not applicable to the object. So reserved copy less than 5. So some people may add it because of the requirement that we have requirements here. A member can reserve at most 5 videos at any one time, but there's no limit on how many movie videos can rent it at any one time. So you may be tempted to add a guard that says less than 5 movie videos at the on the reserve transition, but you shouldn't do that, because this guy applies to the member objects, not to the rental copy objects. So you shouldn't add this guard here. You should add it somewhere else. So mixing up states and events. So return is not a state. Some students drew it as a state before. It's an event. So having transitions with no events, this can happen, right? You have automatic transitions, for example, from the initial state. But most transitions should have events. Having transitions with several events, this is always wrong. Never have a transition with more than one event trigger. So using attributes not in the object, so number of copies. So this is related to the this error, previous error, reserved copy less than 5. So number of copies rented is not an attribute in the rental copy object. It's an attribute in the perhaps in the movie video object. So having states with no outgoing transitions, so overdue and reserved, they should have outgoing transitions. Otherwise, it's a final state. States not in the problem description, like stolen, lost, sold. So sold is not a valid state. Why? Because if it's sold, it no longer belongs to the video shop. You shouldn't have it anymore. It's gone. So you should only keep track of the rental copies that you have in your database. Okay, so any questions? Okay, see you next time.